Okay, good morning, everybody. Thanks for letting me talk about the FYST telescope and PrimeCam and its science goals. The project director of this project is Terry Herder. He is Cornell. The project scientist of this instrument is of this telescope is Gordon Stacy, and the instrument scientist for PrimeCam is Mike Niemek. All three here in Cornell. So first, maybe a little bit of terminology, because it can be a bit confusing about CCAT-prime, PrimeCam, FYST, and all this kind of stuff. So CCAT itself is basically just a legal term, is a corporation. CCAT-prime itself is what we call the project that includes the telescope, associated facilities, infrastructure, and so on. And then the telescope itself is FYST, the Fred Young submillimeter telescope, which is a 6-meter aperture telescope. And the telescope is fully funded and is at the moment actually under active construction. CCAT-prime, our project, is a big consortium. In the US, it's basically Cornell University. In Germany, we have there's a consortium led by University of Cologne, and includes the University of Bonn, Ludwig Maximilians University, Max Planck Institute for Astrophysics, and you have a lot of Canadian universities, and they are combined into the Canadian Atacama Telescope Corporation. They call it CATC, and then sort of CCAT Observatory Corporation and CATC together are basically a joint venture. And so we also, however, include other researchers that are not part of those institutes, but are situated in the United States, Canada, Germany, and Chile. They'd help on also work on some of the science case and instrument development. So to the telescope, the Fred Young submillimeter telescope FYST. It's a submillimeter telescope. It will operate between 200 micron and 1.5 millimeter. 200 micron is something that we will hopefully get in the future. It's not anything in the near term. It has a primary mirror, which is 6-meter aperture. And also 6 meter does not sound very big. Given that we have an off-axis cross-dragoni design, which you see here on the right, the primary beam and the secondary beam are basically about the same size. So the secondary beam is also 6 meter. But the whole design, what this actually gives you is a very clean beam. So you have no obstruction with the secondary. It gives you a large field of view, which is close to 8 degrees field of view. And not only that, it actually is a very kind of almost a plane field of view. There's almost no curvature in there, which makes it much easier to actually build a big instrument there. The surface accuracy of the telescope is less than 11 micron RMS, and the goal is less than 7 microns. So this is to actually allow us to go all the way down to 20 micron observation. The angular resolution that we will get with FYST depends on what kind of instrument you have there, but it reaches between about 12 arc second and 350 micron to about 52 arc second and 1.5 millimeter. And here, that's the what FYST ultimately will look like. So you have this big box here. You have the elevation, housing, 2 mirrors in there, and the whole thing will rotate. And what's not shown here, but it was brought up before by Claudia, they have a high scanning speed, and also CCAT or FYST can also scan at 3 degrees per second, at least in azimuth. So to do subliminal observations, you need to go to a very high and dry site. So with FYST, we will go on near the summit of Cerro Chajnantor. Here you see a Google map. Alma is down here. Apex is over here. This is Cerro Chajnantor. And so we are very close to the summit. We're not going all the way up, but it's very close. At the top, actually, that's where the Tau Observatory will be. And one reason why we want to go up is because if you go just those 600 meters above the Alma Plateau, the atmospheric transmission actually does get significantly better. And you see this in the top right plot. The Alma transmission that you see, it's in pink. And this is for 50%, basically half it's the best weather time they have, which it is about, what is it, about 1 millimeter of residual water vapor. And you see Alma is pretty good if you go sort of these higher frequencies, but there's nothing up at 200 micron. But if you go the 600 meter higher up, the 10% good weather time, we actually get significant transmission at the high side for CCAT or FYST will be. So it's over 30%. I have to say, well, this is towards the zenith. And what does this give us? It's not just the transmission is much better, but also the emissivity of the atmosphere is much lower, which helps a lot to actually reduce the noise of our system. And now with a telescope like FYST, on this big field of view and this high side, you actually have a significant mapping speed advantage compared to a site on the Alma Plateau. This is plotted here on the lower left side. We have on the x-axis is frequency, on the y-axis is basically how many times are we better in mapping speed compared to a similar telescope on the Alma side. And you see at high frequency, we are factors of about more than 4 better than on Alma Plateau. And here are some nice pictures to show you that actually the work is going on. Up here on the top right, that's the FYST site. It's already leveled. They have cut out, dug out the part where the foundation will go. And we also have in Germany, some parts are already welded together and painted. First lights should be early 2024. Not sure if we can get end of 2023, we will see. The instruments for FYST, basically we have 2 instruments. One is PrimeCam. The instrument scientist of PrimeCam is Mike Niemek. And PrimeCam is a modular instrument, contains cameras and spectrometer that you will see up here. And the other instrument is CHI. I have some numbers here, but Nikola will talk about this in a little more detail for her talk. So I just flashed those numbers here and don't go into detail. PrimeCam, it has 7 instrument modules. That's what you can see here in the front. It's basically entrance windows. It has 5 of those modules are cameras. They reach from 220 gigahertz to about 850 gigahertz. And 2 of those modules are spectrometers. And here we have shown these 2 that we call EOR spec, which stands for Epoch of Reionization Spectrometer. They are the spectroscopy or filters that we use there are based on Fabry-Perot interferometer. And in this case, we use actually some special technology here. We use silicon wafers as the mirrors for the Fabry-Perot. That's something different than what has usually been done in the past, which usually were freestanding metal meshes. The spectral resolution we will try to achieve with ER spec is of the order 100. And the frequency coverage of ER spec goes from 210 gigahertz to 420 gigahertz. And it's actually divided into 2 different subarrays, which allows us to actually observe in these 2 bands simultaneously when we are on sky. And maybe in the future, we also will have a chip, a spectrometer on chip module in PrimeCam. PrimeCam only uses about 5 degrees of the field of view that we have available with FYST. As I mentioned before, we have almost 8 degrees. The cryostat that you see here, the whole thing actually is being machined at the moment, and we should get this cryostat beginning of 2022. And we also have the cryocoolers. They have been purchased. They should also arrive pretty soon. What you see here now on the top right is a bit of a cut. So all these modules, they are completely independent. And at first light, we might not have all of them. But so that's not necessary. We can take modules in and out if we need to. So it's a kind of a nice design. So we don't have to wait for that everything's populated. Each of those instrument modules has a field of view of about 1.3 degrees. So it's pretty big. And also the detector arrays that we use for all of those modules, they are based on the MKIT's design. So these are all kinetic inductive devices. And the detector arrays for all the modules, they look pretty much like the one that's shown here on the lower left. It consists of 3 subarrays, and each of the subarrays for each of those modules usually consists of several thousand pixels or detectors. On the right, what you see down here, this is how we subdivide the array for the EOR spec. We have 2 of those subarrays. These are for the lower frequencies, and 1 is for the higher frequencies. The only drawback by doing it this way is they actually see a different part of the sky. But since we mostly will do survey scans, so basically scanning big parts of the sky, this is not a big deal. But now we can actually do simultaneously observation of 2 frequency bands. I already mentioned that FYST will do survey observations, and that's actually the main observing mode that we will have. And we will have we will have dedicated survey observations depending on the exact science case we want to do. And so I will show these science cases in the next slide. The observing time of FYST is subdivided for these instruments for PrimeCam and CHI. PrimeCam is supposed to get 75% of observing time, and CHI will supposed to get 25% of the observing time. So now I'm going to the science goals for PrimeCam. It has there's a list of those science goals. There are many of those. We want to observe the epoch of reionization. The team lead is Dominic Riechers. We will trace the galaxy evolution over cosmic time. That's usually done in continuum observation. The science lead is Scott Chapman. Then Nick Battaglia will lead the science case for galaxy cluster evolution. Then we have a science case for what we usually call cosmology, and one is gravitational waves and the CMB foregrounds, and that's led by Mike Niemak. We also have a science case that's geared toward actually detecting Rayleigh scattering from the epoch of the epoch of recombination, which would be really fun to get. I'm not sure if we can get this one. The lead there is Dan Meerburg. We do some galactic polarization, and the Manush Tahani, she will talk about this science case in her presentation. And in addition, we will also do some time domain phenomena, and there the lead is Doug Johnson. If you want to, after I'm done and you want to have more information, you can go on the archive. There we have already our sort of PrimeCam instruments, paper, science goals, and forecasts. It's available, and at the moment we are working on addressing the comments from the reviewer. So for PrimeCam, all those science goals, they will be addressed by doing wide or deep surveys. Here what you see is a overview. It's basically the whole sky what you see. The background is the Milky Way. That's a Planck picture. And what you see here is a subdivided 5 science cases. The WFS, that's what we call the wide field survey. And that's what you see as this kind of transparent white band that you see here. So we will cover this entire part of the sky for this science case for a wide field survey. And it's mostly cosmology what we do here. Then for the galaxy evolution survey, this is where we try to observe galaxies at high redshift, mainly the cosmic infrared background. So there, those fields are a bit smaller, but we try to get a bit deeper. So we will cover the gamma fields, the Euclid deep field Fornax, and so here also gamma, and eventually maybe also this stripe 82. Then we have additional very deep field spectroscopic surveys. Those are the ones that we will do for line intensity mapping to measure the epoch of reionization. So these are these black ones here. We will try to get the Cosmos field and the extended CDFS, the Chandra deep field, south field. That's the one here. And then we have various other fields for galactic polarization, but Manush will talk about this. And for the time domain, there are various objects we want to observe, but usually they are also part on the bigger survey that we will do. So they will get sort of observing time sort of on the fly. This is kind of synergetic. Here's a table. You get more details in the paper that I mentioned before. Here we have these different surveys that we want to do, the deep spectroscopic survey, the wide field survey, the dusty stuff in galaxies, it is the evolution of the galaxies, galactic polarization, and it's a time domain. And you see here the amount of time we will spend for all those fields. So those numbers are multiplied in by 100, like what we see here. So the wide field that we do will be done in 4,000 hours. And we will cover about 20,000 square degrees in this on this survey. And even for the deep fields, where each of those fields will be done in 2,000 hours, and this we have about 4 square degrees for those ones. So we go really deep for those. Now let's go a bit into those science cases. Let's address them very superficially given the lack of time. So this is now the science case for the epoch of reionization. Here's the lead Dominic Riechers. So what you see here is basically a sketch. On the left side, we have the Big Bang, then you have the epoch of recombination, and then there's nothing happened for quite some time. And then so the first stars and the first galaxies are formed, and so they start reionizing the neutral universe. And then over time, you see that the whole universe gets ionized. Now the trick, we don't really know exactly how this reionization works, whether it's done by very bright and big beams that basically spew out a lot of ionizing photons and they make bubbles and they get growing bigger and bigger and bigger, or if this happens by kind of a Milky Way type galaxy with low star formation, that you get it basically smoother and sort of more distributed. So we try to figure this one out. And we'll do this by doing line intensity mapping. And so for this line intensity mapping, we actually look at the line emission aggregate from many galaxies. So we don't look at individual galaxies by themselves, but we look at basically aggregated signal of several galaxies over large scales, because we're interested where those bubbles actually are forming. We not really necessarily want to know exactly which galaxy is responsible, but in what kind of structure they start building. And for the line intensity mapping, we focus mainly on the 158 micron C+ line. For the frequency range we have for ER spec, this covers the redshift range of 3.5 to 8. But we also will have the O3 88 micron line, and we will have several CO transitions in those observations. And this you see on the left side, but that's what we expect, what it looks like if you get basically a single redshift slice in C+. So you have about a 4-degree field of view. So you see all those observations, and everything should be sort of an aggregate of galaxies. The trick now is because when you have you observe a certain line, you have to actually figure out which one it is. And what you see in the middle plot is, depending on the redshift and the frequency you want to observe, there are actually different types of options you can have. Like all these dashed lines you see here, those are all CO transitions. The red solid line would be the C+. So that's basically, if we are sure we have the C+, that's basically what we trace, which kind of the redshift. And so this one is the frequency band that UR spec is sensitive. And for very high redshifts, we hopefully get then the oxygen 3 line. But it's tricky to really then get a lot out of this morphology, how these bubbles really form. So to analyze the line intensity map, what we will do is we will transform this map, this 2D map, into the Fourier domain, and then look if we find structures. What you see here on the right side is these are several models for how the epoch of reionization is supposed to work. You see on the x-axis, that's basically the inverse, it's the inverse separation between features. And on the y-axis, that's basically power, basically how many objects you have that have certain separations. The dashed lines you see here, that's the sensitivity we can reach with the red dashed lines, the sensitivity we can reach with FYST, with the UR spec, and the solid lines and the broader patches you see here, those are models of what the ionization should look like at various redshifts. And you see that ER spec is always sensitive enough to actually distinguish between all those different models, except if you go to very high redshifts, so 7.5, it depends on which model is correct. We might not see the ones that are all the way down here. The next science case here is the galaxy evolution over cosmic time. And that's a science case that actually is going on for the last probably 40, 50 years. And that has to do with the detection of the cosmic infrared background radiation, the CIB. About half the radiation that's spewed out by star formation is extincted by dust, and then dust re-radiates in the infrared. So, but we would like to find out what type of galaxies actually then re-radiating all out this infrared background radiation. And so there's many observations have been done. They try to really resolve those targets and see what kind of galaxies we have. Herschel has tried this, for example, that's what you see here in the middle plot. This is a observation by Herschel, and Herschel is confusion limited. On the right side, you see what FYST would detect at 350 micron. So you see we will get a much better resolution. So with the 350 micron camera that we will have, we actually reach about 2.6 times deeper than what Herschel can do. And what we then try to figure out is we do this over a bigger redshift range, and we try to observe the CIB basically from the first billion years up to cosmic noon, where cosmic noon is basically where you have the peak of star formation in the universe, which is at redshifts about 1, 2, 3. So we try to improve a lot of the Herschel and hopefully get out and resolve really those galaxies to high redshifts and long wavelengths. And we do this by doing these large and deep surveys. And you need to have both, so to speak. You need to have large surveys, because if you have a small survey, what can happen is what you see here in the lower left is that you can be in some of those parts of the cosmic web structure, where you actually are you get biased because you see those filaments where all these galaxies, you have all those streams. Or if you happen to be in one of those bright where you have clusters, then you have also bias. Or if you happen to be on a void, so you have to be careful. So that's why we have a very large field that we want to do with FYST to do this kind of stuff. And that's also then shown here on the right. So let's maybe focus on the top plot here. Oh, sorry. What you see here is the redshift on the x-axis and the star formation rate on the y-axis up here. And this basically shows you what kind of galaxies you would detect, what kind of star formation rate you would be able to see over this redshift range. So if you have galaxies of maybe a few or a few hundred star formation stars, solar masses per year, so this will be basically you will see those in the white patch here. Those ones you can see with various observatories. The issue is if you want to see these more higher star forming galaxies, then it's getting trickier and trickier, because they are not that numerous, so they are getting rare. So you have to actually get large fields in order to see those, and you have to get the sensitivity. So what we will get with FYST and PrimeCam, it's the red bar here. So this gives the sensitivity, and we will see basically everything that's above. The dashed line you see here, for example, an ALMA observation, that's the green dashed line, that's the sensitivity that it can reach. But the issue with ALMA is they just don't have this large field. So they wouldn't actually see stuff up here, because actually they don't cover a large enough field. So I skipped this one down here because of time. The next science case we will do is observing galaxies and galaxy cluster evolution. And we will do this by observing the Sunyaev-Seldovich effect from those galaxy clusters. And just a reminder, the Sunyaev-Seldovich effect, what happens there, you have a CMB photon. So it gets into this cluster where you have these hot electrons, and then you have scattering from those hot electrons. So these photons get shifted from the Rayleigh Jeans part of your black body function into the Wien part, and then you get basically the higher energy photon will then hit your detector on your telescope. So what this actually does is it shifts your black body function a tiny little bit. It basically moves part of your Rayleigh Jeans, part of your black body function to the.
You have 2 minutes left.
Oh, okay. I have to speed up a bit. It basically moves one side of the function to the other one, and so you get this feature here. And by then observing different types of the SC effect, the thermal, kinetic, and the relativistic, you get different properties of those clusters, which then can inform you about these properties of the intercluster medium and what kind of profiles you have. And this can inform you about AGN feedback, cooling mechanisms, and actually how star formation is being affected and how maybe star formation is being quenched if that happens to be there. And this is a plot. So with FYST, we will see all these blue parts down here that will not be able to, others cannot see. They only usually see this one. The cosmology section, okay, I get pretty quickly through this one. It's basically try to search for gravitational waves, and that has to do by observing those basically B modes. The B modes are imprinted is predicted by inflationary theories, and they are imprinted by these. Let's see where I have it. let's see, they're predicted here. I think they generate these tensor modes, tensor perturbations. But the B modes, you have to be careful to do this because when you do observation and polarization observations, you can get fooled by foreground dust emission. And that's another part that we want to do. That's then here we have to actually really understand the foreground dust to be sure that any B mode we see is actually from the CMB. And Rayleigh genes, that's basically, okay, why is the blue sky? It's the same thing happens at the epoch of recombination. When you get neutral hydrogen and helium, you actually do Rayleigh scattering of the CMB photons. And then what happens then is those scattered photons, you will actually sample different surfaces of last scattering at different frequencies. So if this can be detected, it would be really nice, and we can sort of see what if the models are correct. So the last topic here is then time domain.
It's time to go to your conclusion.
Yep. So this time domain. So this is synergetic stuff. We will do young stellar objects, and basically my conclusion is basically this one slide. This is the paper to look up more the details, and we also had a collaboration meeting, and that's the URL. If you want to have information, you can find papers on this URL. Okay. Thank you very much.
We have time just for one quick question. Quentin Salomé.
Yes, thank you, Thomas, about your presentation. I was just wondering, because you target to reach 200 microns, is there the possibility in the future or the plan to extend to higher wavelengths, smaller wavelengths, sorry, to reach the 158 microns C2 line in the local universe? Or maybe it's not possible at all due to the atmosphere. I'm not sure about this.
As far as I know, you won't be able to see it from the ground. 158 micron is really, the atmosphere is really bad.
Okay. Okay, thanks.